And then the time is going to be, well, whatever time it was when the pulse got sent, plus how much time it takes to get back to Earth, which would be how far away it was sent divided by the speed of light. We're dealing with Doppler shift with electromagnetic waves that travel at the speed of light.
So by received, that means that it got sent back to the Earth.
Yeah, S prime sends out this pulse, and that eventually that wave makes it to Earth. And on Earth, somebody sees a machine that goes beep, so they know that they've got the second pulse. All right. From switch notation in the middle. All right, so the signal from S prime's point of view, from the rocket's point of view, the period, the time between pulses being sent is TE prime. From Earth's point of view, the difference between the pulses, between receiving pulses, is this. So okay. Realize my notation is not messed up. So the period of receiving, R for receiving, not rocket, that's what messed me up. How often the Earth is going to get it is going to be TE plus V over C TE. Well, I can factor TE out. I'm left with TE times 1 plus V over C. Which, as we know, is the time between the signal being sent out from Earth's point of view times 1 plus beta. Well, if we want to translate between the two reference frames, I know that this would be the time that's elapsed from Earth's point of view between sending out the signals, but that's different than the time in the rocket ship. So there's a relationship between TE and TE prime because of time dilation. And so this is equal to gamma times TE prime, 1 plus beta. So this is the period from the rocket's point of view. This is the period of receiving from the Earth's point of view. So the period of receiving is equal to gamma period from the S prime's point of view, the E for emission. It's unfortunate that I'm using R and E for receiving and emitting when I'm now also using Earth and rocket as an analogy there. Anyway, subscript E for emission, subscript R for receiving. Times 1 plus beta. Well, what is gamma in terms of beta?
1 over beta.
No.
Square root. Is it 1 over square root of 1 minus beta?
Almost.
beta squared.
Yeah. Times TE prime, 1 plus beta. So the time it takes to receive it is equal to the time from the moving reference frames, how often they send it, times this other mess. Well, I know that 1 plus beta over the square root of 1 minus beta squared is 1 plus beta times 1 minus beta, 1 plus beta, which is the square root of 1 plus beta over 1 minus beta. So the period being the time between receiving the signal is, so from the point of view of the receiver, is equal to the period of emission from the point of view of who's emitting times the square root of 1 minus beta over 1 plus beta over 1 minus beta. I know the period is the same as the reciprocal of the frequency. So 1 over the received frequency is 1 over the sent emitted frequency times the square root of 1 plus beta over 1 minus beta. Or in the more traditional form, the frequency of the observer, that which is being received, the frequency of the observer is equal to the frequency from the source's point of view times the square root of 1 minus beta over 1 plus beta. The observed frequency is in the reference frame of the observer. The source frequency is in the reference frame of the source. Now, this is S prime is moving away from S. As it moves away, I would expect the frequency to drop. And so we have a minus over plus because the frequency is getting lesser. The same is true with sound. In terms of, as something passes, the frequency goes, so the frequency drops as something passes. If you think about it and you realize, oh, they're getting closer to each other, frequency should increase, well, then flip the signs. Now, a difference between sound and light. For the situation where they're getting farther from each other, and I know the frequency is going to increase, so for sound, the frequency of the observation is equal to the frequency of the source times speed of sound minus speed of the observer over speed of sound plus speed of source. That is really need to come up with different letters there. So this is frequency of reception, frequency of emission, reception, emission. Right. Now there's clearly a difference. We still got the plus minus. We've got a relationship in there. I can multiply top and bottom by C and I'd get a C, or either one. I'd multiply top and bottom by C in here and I'd have C minus V, C plus V. So I can have somewhat of that form, but we have this extra square root in there, which is an implication which comes from the speed of light being the same in any reference frame. So if in sound, I'll just be still. I'm the observer right here, and I got a car that's honked its horn, and the sound waves are coming at me. If I ran towards it, it's going to appear to me that these molecules are coming at me faster. So for sound, there's a relative speed there that, because these are actual particles that are moving, there's a wave moving towards me. If I ran towards the wave, its speed seems faster. Sound. With light, on the other hand, if I have light waves heading towards me and I run towards it, the light is still going to seem like the same speed as if I'm standing still. Frequency changes, period changes, wavelength changes, but the speed seems the same to me, because the speed of light is the same regardless of the reference frame. And that's the implication there. Questions? And again, RE for receiving and emitting, or reception and emission. Receivedness. And emittivity. All right, on that note, have a nice weekend.
Is there an analogous version of a sonic boom to light?
There is, called Cherenkov radiation, that, we talked about the speed of light, you can't pass the speed of light. That is the speed of light in a vacuum. But if I send the light through a gas, such as air, light is constantly getting absorbed and emitted. So light gets sucked in, an electron might move to a higher energy level, that's not stable, the electron drops down, and light gets emitted out. So the speed of light, so sort of the drift speed of light gets slower in certain materials, and through certain gases, certain materials. And it is possible then for something to exceed the speed of light in those situations. And there's something called Cherenkov radiation where light gets slowed, the light gets emitted, you have a charged particle moving, it's emitting light, but the charged particle is moving faster than light is moving through that medium. And what ends up happening is you get this blue glow. And that's sort of at least the pictures I've seen of Cherenkov radiation. So that's the equivalent. You don't get the buildup on waves so that you're blinded. I don't think it's weaponized. But I would not be surprised if someone's working on that. But generally, the slowest they've gotten light to go through a medium is, it seems like I read it was like 6 meters per second through some medium. I don't remember what the medium was though. Certainly.